This is our third and final discussion of the Motion Lab and the Advanced Manual. This green and black manual right here is the current Advanced Project Manual for RSLogix Studio5000. And occasionally we upgrade, we might change the color of the cover. If you have older versions of the Advanced, and at one time it came in 2 documents, you could also watch these videos because the labs in those manuals are pretty much the same as the current one, just missing a few of the updates. So let's jump in and do part 3 of Motion. Welcome back to Motion, part 3, driven by the Logix engine. Creating a jog routine. If you can hear the steady hum in the background, that's the Ultra 3000 servo drive. Unfortunately, we're going to have to listen to that while I'm recording, otherwise I can't do this online. And you can see on the screen that we're in the remote run mode and our I/O OK light is solid green, meaning that the Circos module sees the drive and everything is good with the drive. In the lab manual, I had you add a new subroutine to the main routine. I'm going to close that routine. I'm going to open up the main routine. You can see there's our new subroutine, that JSR's jumped a subroutine to the jog subroutine, and then we'll open up the jog subroutine. Remember that you can have all of these routines open with tabs down here so it's easy to jump back and forth. In the jog routine, we created a rotary jog forward push button, attached it to input 6. I'm cognizant that your hardware may be completely different and you have completely different I/O. But remember, this is an advanced subject and we assume that you already are well familiar with I/O structure. And if you ended up with universal I/O, meaning fake I/O or simulated I/O for your push button, and you have to toggle it right directly in the database from your keypad and mouse, that works fine. The next 2 tags are tags from the rotary axis status. Axes homed and servo action. If you press the jog forward push button, and the axis is home, and you can see here that it's not. I'm homing it right now, and now you see everybody's happy. I'm going to expand this instruction. You know, we discussed this in the manual. Direction 0, speed 360. Well, it could be anything between 10 and 2000. I just put in 360 because of the units that we're working with. Do you remember what the units were that were specified when we set up this axis? That's correct, degrees. What does 360 units represent? If you remember, it was 360 units per 1 revolution of the shaft. We have it set up so we travel 360 units for every rotation of the shaft. So that's basically 1 revolution per second. 360 speed units per second. That would be 1 motor rotation, 1 shaft rotation per second. The rest of this information is of no real interest other than you need to fill it in. Typically, I always put 0 for lock position and none for lock direction. With none selected, this value is somewhat irrelevant, but you have to put something in there. So we'll collapse that instruction. And then, of course, when you let go of the rotary jog forward push button, which it's not pressed right now, so you can see this is true, we're going to do a motion axis stop. And there's not much to a motion axis stop. You did a couple of them in a previous lab. You did it in the direct motion commands. We're going to do a stop type of jog, and you know you could pick all, and it would take care of it. In this case, we just picked jog because we want to stop the jog. And as I said, this is the standard instruction to stop a motion before it is complete, or in this case, a motion that has no completion. When you issue a jog command, it just keeps running in that direction until you tell it to stop or it runs out of travel. Since we have nothing hooked up to the output shaft of our motor, it would just jog for hours and hours until the power failed or you stopped it. The answer to the question in the manual, without this instruction, what would happen when you release the jog push button? Nothing. It would just keep right on jogging. And then, of course, we all understand TONs, on delay timers, and looking at that code, you see that if the jog forward push button is pressed and input 6 is true, on, and that timer is not done, then the timer times or increments. And it's set for 1/10 of a second, 100 1/1000ths. Every 1/10 of a second, that done bit goes high, the rung goes false, and the timer resets. So basically you have a timer that's free running, and every 1/10 of a second it changes state. And you can see right below it in the last rung, the enable bit from that timer is going to toggle, and that rung will go from true to false and back to true every 100,000ths of a second, or every 1/10 of a second it will be false for one scan and execute the motion change dynamics. This is a very cool instruction. It allows you to change things on the fly. And if you compare these parameters with the parameters up here, you see that they're relatively close. You can change most of the parameters in the move instructions with an MCD. In this case, we are using the analog input channel 0, that's why we added the analog card, to provide the speed for the jog. So every 1/10 of a second, the jog is going to have its speed, which started at 360. It's going to have it refresh to whatever this value is. Now that's a big jump, 5120. I'm going to turn that down, and then down to 0, and then back up a little bit. Just a very slight turn of this pot, and I have a 10-turn precision pot with a vernier dial on it, so I can get a little bit more accuracy when I'm playing with things, and it has a lock on it. That's not necessary. Your trainer, if it has an ordinary turn pot, meaning that it turns like 270 degrees for the full sweep, it still will work fine. Just don't turn it real fast, because you don't want to overdrive the motor. In the next section, we'll put a limit on how fast you can jog it. So I told you to hold down the rotary jog forward push button, adjust channel 0 potentiometer to increase or decrease the jog speed. All of these instructions are transitional, meaning that once the instruction is enabled, you must cycle the run condition to reinitiate the instruction for any changes to the instruction to take place. Once the motion axis jog instruction goes true, you have no more influence over it unless you let the run go false, change a value, and then have it go true again. Now in this case, the motion change dynamics can directly change that instruction. That's why it's called a motion change dynamics. What is in the logic to allow the analog input to change the speed without releasing and pressing the jog button continually? Well, the MCD, which is toggled every 1/10 of a second. How would you modify this logic to limit the maximum to 3600 degrees per second using the full swing of the analog input? In other words, for 1769 IO, the analog input is going to be 0 to 32,767. How would you add code? What would you put in here so the full extremes would be 0 to 3600? As you can see, I paused the recording. I made the edits, and now I'm back. I added a divide instruction, unconditional, that divides the value, the integer value from channel 0 data by a factor that I calculated. I created a tag, degrees per second, and you can see that 640 equals 73 degrees per second. As I increase the value, you can see that my maximum value is 31,360. It's not 32,767. That's because my voltage dropping resistor in series with the potentiometer is not of the exact value to give me exactly 10 volts across that potentiometer. Remember, we have an analog input of 0 to 10 volts. Now, I could always fudge that to make it look 32,767, but it's really irrelevant. In order for you to come up with source B, while you're not jogging, rotate your potentiometer to its clockwise limit, like I just did. Divide that by 3600, and that is your source B. And you can see that the result is 3,586. Not exactly 3,600, but pretty close. And if I wanted to fudge that 8.74 a little bit, I would lower it. We'll do that just for grins. So we got 3586. Let's decrease this to 8.74 and see what that does for us. This is really a subject for the analog lab. Well, we need a little bit more change than that. I probably could have calculated. Matter of fact, if I did 31,360, we'll just do that. We'll get the calculator. 360 divided by 3600 equals 8.711. So we'll throw that in there. We'll round that up just a little bit to hedge our bets. You can see this is definitely not rocket science. And once you see these type of data manipulations, it's a no-brainer. 35,999. My goodness. Oh, you know what? When I changed that fourth significant digit to 2, I actually lowered it from it would have been 3,600. So my apologies. We'll make this, I bet we hit 3,600 pretty close right on the button. How about that? So you understand what we did now. And of course, we created this new tag, degrees per second, and then we moved that tag in here for speed. So instead of using local slot 3 input channel 0 data for speed for the motion change dynamics, we moved the degrees per second in. We massaged, if you want to call it, the raw value, and then moved it in. So now, if I crank the potentiometer all the way up to maximum, I'm not going to jog faster than 3,600 degrees per second, which is still flying. That's 10 shaft rotations per second. In the real world, this is going to be attached to some kind of a load, and the actual mechanical motion, after it's gone through gear ratios on the actuator, that's actually going to determine your jog speed. Many people they add to the screen on your system, the operator interface terminal, they add a button to change the jog speed. And a lot of times they actually use the length of time that you hold down the jog button. So you press down the jog button, and the longer you hold it down, the faster it jogs. And if it gets going a little faster than you want, you just release and press it again. So you can jog it and speed it up. When it gets close, let off, and then jog in slow. We're not going to do that in the lab, but I think you can appreciate how you might do that with a timer, with using a ramp. And as the timer accumulates, you can use that to keep refreshing your jog speed. Okay, open up your tag database. It really didn't matter where you put the tags. The I/O tags are going to end up in the controller tag database, as well as these two tags, because all of these devices are external to the processor, meaning that they all are dealt with across the backplane. The motion group, the rotary axes, and of course all the I/O, those are predefined, module type defined from electronic data sheet data types. Typically, I put everything in the program tags unless I know I'm going to need it in other programs. Because you remember from past labs, and I'm going to open up program tags now, that these tags are only accessible in this program. Okay, and of course we could change the name of that. So if we created additional programs, each one controlling an axis, we could repeat all of these tag names within that program, because this group of tag names right here is not accessible to any other program but this one program. And remember, you can have up to 30, well actually you can have up to 100 programs in each of 32 tasks. However, we're not doing anything that complicated. Now, as I said in the manual, that these are the edit tags views. You should be able to recognize every tag in these two lists, the controller and the program. You should understand what the value in each column means and its relevance. And if you do not, you need to go back to the beginning and do some of the exercises, some of the labs over again. As a programmer, you will write the same instructions over and over again, just like typing the same words over and over again in a word processor to create new thoughts and new ideas. You have to become proficient enough with these instructions that you really, just like when you speak or you write, you're not really thinking of the meaning of each individual word as you type it or write it. They just pop in from habit of use. It is difficult to use words that you are not sure of their definition. So if you're not sure of these instructions, you need to do some repetition, and repetition is an excellent teacher. They say 10 times through anything and you will remember it. It won't kill you to go through some of these labs 10 times until you're polished with very basics. And of course, even though I have most of the tags in the program tag database, you can cut and paste tags from one database into the other, with the exception of the actual module defined tags. So all of these tags could be moved into the controller tag database. However, if we look at the controller tag database, none of these tags can be moved into the program tag database. Now, one other thing I think I pointed out before, that is, you see these tags are module defined. These are not. They're data types that are predefined, axes, servo, drive, and motion group. But these show white background because you can change the name. You can always edit the properties of that tag, and you can change the name. I'm going to cancel that. We don't want to change the name. In the lab, I also ask you to copy and paste some of the tags from one program, from the program tags into the controller tags, and then delete those same from the program tags. The reason I said copy and paste instead of cut and paste is it's a little safer if you copy paste, then go back and delete the ones that you copied. But you can cut and paste if you like. And then I had you test your program. Does it still function? Well, it should have. Then I had you return the tags to their original database before continuing. Next, I had you add logic to use any unused switch that you still have available in your hardware demo to provide a jog in reverse. I have a solution in the manual, but I ask you to try it for yourself without looking at my solution, and then if it's just not working for you, edit your logic to match that on the following diagram that's in the manual. Let's go through these changes. In the first rung, the only thing that we did was we added the not condition for the reverse push button. We already had a forward push button, so we created a new tag for the reverse push button using an unused input 7. Other than that, this rung remained unchanged. Then we duplicated this rung and just changed these two instructions so they were opposite. That way you can't press both the reverse and forward jog buttons at the same time and get an interesting result. These two instructions are identical, so the only thing different was we added the reverse push button as a not, and here is a true if on, forward is true if off. So this is a duplicate of this rung with just the buttons reversed. For the motion axis stop, we had to add the reverse in, so if both push buttons are not pushed, then we stop. I guess you could do an either in the positive node or both in the negative, depending on how you like your Boolean algebra. And then, of course, our timer, we needed to add that either the forward or the reverse push button would give us our pulses to execute the motion change dynamics instructions. Our divide instruction did not change, it's still degrees per second. Before, we really didn't need this button in there before, but now we do because we want to differentiate between forward and reverse. Still the same timer, so we could have incorporated this into one rung with this as a common condition or permissive, and then branch to this MCD and branch to this one. Here we negate the degrees per second, otherwise we would not be going in reverse. Now there's many other ways to do this. I probably have personally seen at least a half a dozen different ways of doing forward and reverse jog. Some people use a toggle switch to enable the jog, or rather I should say they use a toggle switch to select forward reverse and then only one button for jog. That's another way to do it. I like separate buttons myself. I think it's more deterministic. And you could have accomplished this with only one MCD instruction and some extra tags or two outside of the MCDs to massage the values before they are accessed by the MCD switch. The 100/1000ths preset allows a change in the jog speed every 1/10 of a second. It can be longer or shorter. Experiment with a preset for the speed adjust TON and observe the results. I lowered it to 1/1000ths of a second. In other words, I dropped the time base right down to 1, and it still functioned. But what could play into the actual update rate with a controller that is executing large routines in many programs? Well, how could that play in? The idea is to have the rungs executing the MCDs alternate between a true state and a false state and back again to execute the changed value for the speed. Remember that it's going to toggle this bit every 1/10 of a second, but it is possible that because of that time base for that timer, if it was set to 1/1000th of a second, that the timing of your continuous task and the execution of the routine, it could actually see this as true multiple scans in a row, or not true for multiple scans in a row, simply because of the synchronization. 1/10 of a second works out great. However, you can experiment just for grins. Next, we're going to do motion axes move instructions. And the motion axes move instruction is the most common instruction used in the motion instructions. And this, in the manual, I showed you some of the help file because to give you easy access to it while you're doing the move instructions in the lab. You could have opened the manual and found it yourself. Or you could have went up to instruction help. Right here, help, instruction help. Scroll down to motion move instructions. Drag this, let's see, motion move there on the top. Clicked on MAM. And then scroll down and read all this for yourself. It's a little easier to read it if it's right in the manual where you have easy access to it rather than taking up screen space and moving back and forth. They got nice diagrams in here, so the help file is very good for the instructions in RSLogix 5000. For the motion axis move instructions, we had you create a new routine named indexer, and then in the main routine we had you add a rung to JSR to the indexer and to edit the existing jog JSR rung to use an unused switch that you could toggle back and forth between jog and indexer. We want to reuse at least one button possibly that we used in the jog routine. Plus, in the real world, you would not have the jog routine enabled while you were running the regular program. So in this case, we're considering indexer our actual production program, and jog is something that you would do in the maintenance or manual mode. I guess you could call this jog or indexer selector switch, you could also call it auto manual. when it's on, that would be in the manual mode, and you could run the jog subroutine. So I had you add this switch to the jog subroutine JSR, and then the NOT for that same switch to enable the indexer subroutine. So let's go to the indexer subroutine, and we'll close the jog routine. We don't need that. Go to indexer, and in the indexer we reused our divide. We didn't move it from the jog routine, we just copy and pasted it, created a new tag, indexer speed, and then we also used this rung simply as a way for you to view the actual position of the encoder as we are moving through the sequence of the index. So this rung really doesn't do anything. We're not using the position tag. This is just here so you can view the position that the drive is providing. And then we added this tag, run index, to the last unused input on our hardware demo. I only have 10 inputs connected up to that 16-point card, and I have 10 outputs connected up to the output card. Then I have 2 analog channels in and 2 analog channels out. I'm using the hardware trainer that I call the advanced trainer in one of the videos on the YouTube channel. Okay, so here's our motion axes move. Let's expand one of them. They're all the same other than most likely the position. Each one has to have its own unique motion instruction instance of the data type motion instruction. They all use the same axes, but each one needs its own separate tag structure. So this is rotary index 1 motion axes move. For speed, we are using indexer speed. And of course, indexer speed is provided right here from channel 1 data. Now, channel 0 data is for jog. Channel 1 data is for our indexer speed. And you can see that our factor isn't exactly the same. In other words, we got it down to, I think, 8.711. We'll go change that one. It really doesn't matter. And you probably would have used a tag here instead of a constant, simply to allow you to change it without going to the edit mode like we just did. If I think there's any possibility that I need to change a value on the fly, and it normally is put in as a constant, like source B, actually either source or A or B could be a constant, I create a tag and then put the value in the tag. That way I can edit the tag without putting the rung in the edit mode. Okay, so moving down here, all of these are the same. Notice that we have 2 tags or 2 booleans here that are important, the in process and the process complete. So when this process is complete, then it starts the next motion axes move. As we go down 3, you can see that rotary index 3 motion axes move. When the process is complete, then it starts rotary index 04 motion axes move. I had you execute this, and by the way, I said when it comes to these switches, if you do not have enough switches to connect to inputs, you can use switch bits instead of switches. In other words, you just create tags that aren't alias to an actual I/O, and you have to manually toggle those on and off. So this particular tag in the main routine, this could have had the same name and just been a boolean, and you toggle it, it goes on, you toggle it, and it goes off. That's how you switch back and forth between your 2 routines. You can do that with any of the I/O that we have. You can do the same thing here. That could just be run index and be a boolean program tag, and you right-click to toggle it on, right-click to toggle it off. So I had you add those rungs we just looked at, and the only difference between those motion axes move was the motion control tag and the permissives. Then I had you add the 2 rungs at the top, one that actually divides channel 1 by my factor of 8.744. I changed it to 8.711. It's going to vary from equipment to equipment, and then the tag that displays actual position. Now, rotary.actualPosition is a very commonly used tag because quite often you want to know where the actuator is at. I said you might have to home the axes And then I had you turn on the run index bit or switch. And in our case it's 9, so I'm going to flip that on, and the motor starts moving. I geezered down the, or geezered up, whichever way you want to look at it, with the little geezer buttons up here. And now we're going to turn on the indexer, and you can watch these going complete and cycling through. So I turn on the index, it starts moving. This one is in process. You didn't see it say in process because it happened so fast. Now watch what happens when I turn off the index. You see the process complete? You get some unexpected behavior. That's not the behavior that we want. One more thing that I had you add in the lab was I had you add an OTE, index running, and we alias that to output 4. Turn on the run index bit or switch. The light should come on and the shaft should rotate through the positions. Did the shaft reverse to stay within the 0 to 360 degrees that our positions were within? Yes, they did. They did because we have move type 0 selected, which is absolute. So absolutely from home, 90, 180, 270, whatever, and as long as it's less than 360, well, look at our sequence. We went 180, then 90, then 270, and then back to 90. If this were incremental, then we would have moved incrementally 180 degrees, and then 90 more, and then 270 more, and then 90 more. It would not have reversed. They would have been incremental moves in the positive direction, whereas these were absolute moves. And with absolute positioning, there is only one point that is 90 degrees, 180, 270. Whereas if you're moving incrementally, they would all have been positive moves. And the position is incrementally in a positive direction from the current position. So the first motion axis move would have went from home to 180. The next one would have went back to 90. You know, it would have went reverse 90 degrees. And then the next one would have went forward 180 degrees to the 270 position, and then 180 degrees reverse back to the 90 position. Now if we change these to incremental, you're going to get an entirely different behavior. I'm going to change these, but I'm going to pause so you don't, well, I'll just do it while you're watching. I'm going to geezer up a little bit, and we'll make the move type 1. Finalize all edits. Okay, now I'm going to rehome just so I can declare the home position. Okay, my little tie wrap is pointing straight up on the motor. Now I'm going to clear these manually so it's reset back to the beginning. I'm going to geezer down so you can see all of them, and I'm going to turn on the indexer, run indexer switch. It went 90, then it's going in the positive direction for all of the moves. It went in the positive direction for all the moves, and if we look at actual position, we'll geezer back up here. Actual position shows 630 degrees. Now I'm going to turn that off. I'm going to home again. And now we're back to 0. Now it's not exactly 0, but 0.467, whatever, that's acceptable in the way that we set up our axes. So now I'm going to run that again. I'm going to clear it. The next part of the lab, I actually have you put in logic that clears this automatically. Now, I didn't have you do all this in the lab, but I think it behooves us to do this. Okay, now it's all reset. I'm going to run index again. Watch the position. I don't think you can, well, you can watch it, but you can't see all of this at the same time. That's unfortunate. We'll geezer down here a little bit. Well, I don't know if you're going to be able to read the position. So we'll go ahead and run it. And unfortunately, the update time on the screen is not fast enough that you can actually see it keeping up. So it went up to 630 degrees. So that's 180 plus 90 is 270 plus 270 is, well, okay, so you can see that it's incremental. In the lab, I said to, will pressing the start index push button start another sequence? Try it. Well, the answer was really no. It doesn't really start it from the same position. That's because the process complete bits are left on. So it's not a behavior that you want. We're going to add more code to make this look right. So I'm going to pause, add the code, and then come back. The first change we had you make was to remove the run index push button. Well, it just said run index. I edited the tag name and added the underscore uppercase PB just to make it more explicit. We removed that from this rung and put it in a new rung. We created a new tag called index complete. We had that turn on the light that says the index is running, and then we use that tag here to run our sequence of indexes. And then, because this is a momentary push button, we seal it in with that same tag. So we start the index, and what stops the index is when the index is complete. At the bottom of the logic, we added this rung that says when rotary index 4, motion axes move, process complete bit comes on, that would be at the end of this move, then it unlatches or resets the process complete for rotary indexes 1, 2, 3, and 4, turns on the index complete bit. And of course, one scan later, this is going to be false and that bit's going to be back off. So this is scan dependent logic. So you could actually add it in here as a branch, the last branch. This is scan dependent logic, so if you were to move this rung to a different place in the program, it may not work the same. So let's execute that. You can see them going on one at a time. 3 is on, and when 4 completes, you didn't see it because the screen doesn't update fast enough. I would have to lengthen out those moves to give the screen time to follow. But you can see it does reset everything. So they're all reset, and the index complete released this bit. So if I push the button again, it runs through the sequence again, and when the sequence is complete, this bit will go high, which makes this false, and that then releases this logic, so this bit goes off, the run goes false, and we're ready to run it again. The next step of the lab, what can you change to have it run continually until you press a stop index push button? And I'm going to pause, make the edits, and then come back. I made the changes. I took the index complete out of this rung, moved it down here, then I added the stop index button. Now the problem with stopping the index this way is that when I press that button, this bit goes off, so this rung is now false, and so this rung just flat stops executing. Here I stopped it. It must be in progress. You see, it was just switching over. We completed rotary index 3 motion axis move, which enabled this one, but you see this one is done, but it's not actually complete. It just stops it right where it's at. See, this never completed, so we didn't get an index complete. And if we restart it, see, it's left in kind of a unusual situation. Now it's going to go back and sequence correctly. That doesn't work out perfect to do it that way, but it does stop it. So we're moving in little steps there. You should have already done the lab, so you already know the outcome. You're just listening to the discussion. Stop the index as soon as the first motion axis move is executing. When does the motion stop? It stops at the end of that motion axis move. In other words, once the dog is turned loose, the dog is loose. However, because the rung is no longer true, it doesn't execute the next one. Press the start push button. What happens? Well, it restarts again. Does it start the index sequence at the beginning or continue from where it is stopped? It continues from where it stopped. What would be a better name for the stop index or push button considering what actually happens? I would say pause index or suspend index. Pause, I think, is better. How would you modify the logic to allow the sequence to complete after pressing and maintaining the stop index or push button? In other words, you're going to press the stop index button down and hold it down. Now, I noticed that my tag name for the stop indexer is actually stop index _ push button on the screen, and it was different in the manual. It really doesn't matter, but I just didn't want you thinking that one or the other was wrong. It really doesn't matter what you name the tags. So how would you modify the code? So I'm going to pause, make the changes, and then come back. I've done several things. One is I put the index complete, not complete, in parallel with the stop index push button. That way, if I push this button, but the index is not complete yet, it's going to keep on running the index. If I hold this button down during the one scan, when this instruction, the bit goes on, but the instruction goes false, the rung is false, drops out index running, then, and we really don't need that there. I just left it there. Another thing I did was I changed these back to absolute. And for my positions, I have 180, 90, 270, and then back to 0. When you do this, you should home the device, which is going to give you a position of 0. And you see I'm in 0 there, so if I hit home, it goes through the process, a little motion, it doesn't go far. Actually, it went all the way around and comes back to the marker pulse right there and is back to 0. It's unfortunate the screen updates so slow. We are on RS-232 instead of Ethernet, and so we have a couple things working against us. Now, if we wanted to, even with RS-232, we could put a time delay between process complete and starting the next motion axis move. We could even put in, well, we could put a little time delay in each one of these and give us time to watch our display here. So I'm going to start this. Remember, we're going from 0 to 90 to 270 back to 0. Well, so we're going 180, 90, 270, then back to 0. So if you watch the position, so it's jogging. I'm going to hold down the stop index push button, and you see it goes false there, but the index complete not is still true. So it's continuing until it's completed all of the moves. And then when we get the index complete, it will drop out the index running and stop. It's still running. I slowed it way down so you could watch the position with a little bit more accuracy. Very slowly moving. Now it's back to 0. and the index was complete for one scan. You didn't see it, but it unsealed or knocked out the index running rung and it stopped. Now if I speed that back up, so if you look at the speed here, right here it's about 15 degrees per second. So if I bump that up to, something a little bit faster and do that again, now I'm running the index, it's just flying through it. So if I hold down the stop index push button, you see it goes back to 0 real quick. We didn't have to wait long. I also had you add 2 additional motion axes move instructions to get the actual index up to 6 moves. I'm going to pause and add that code. Okay, you can see that I added 2 more motion axes move instructions, and we had stopped right here. This scrolled so slowly with rotary index 4. So rotary index 4 process complete starts this motion axis move. Now I don't have values in here, so I do need to put in a position, so I'm going to have to go back into the edit mode and then scroll down and put some positions in these 2. This one was back to 0. We'll make this one a little bit larger. We'll make it 720, which is 2 revolutions, and then we'll go back to 0. That'll work. Finalize all edits. Yes. Accepting the pending edits of programming program. Very slow process with RS-232 38.4K. Now this is a little difficult to watch, so I'm going to scroll down here so you can see the process complete bits. Another thing you want to make sure you do is add in the unlatch, which basically just resets the bit to 0 for 5 and for 6, and then you want to use 6 to do this process. Now when I first did this, I forgot this was still 4, and I thought, why is this not completing? And it was not doing the last 2 moves. Well, obviously that's the kind of mistakes I make. I know you all don't make mistakes like that. So let's start this and watch it. I'm going to home first. Now I'm going to run the index, and we're running at a higher speed now, so it should go fairly quickly. You won't even see all of them turn on, and it'll reset. Now the last one, because it's such a long move, in other words, rotary index 5, that's 720 degrees. That's 2 revolutions from the home position. So the last move, rotary index 6, is 720 degrees backwards. In other words, it's going back to 0. But you'll never see that bit come on because it's only on for 1 program scan. The index is complete. Now I'm going to hold down the stop button. And you see it reset, so it stopped. Everything is working fine. Just for grins, in other words, just for smiles, we're going to get our geek on here, our nerd on, if you like, and we're going to start adding some lights. We don't really have any outputs to run. In other words, we don't have anything to make any kind of real motion, but at least we can do the lights. So I'm going to pause and add the code. I added these 5 rungs. I did not have 6 unused lights, LEDs, so I could only do 5, 6, 7, 8, and 9. I have 10 outputs, and 0 through 4 are already used. So let's run this. I'm going to do home first. Home complete. Now let's run the index. And of course on the screen you can't see the lights updating simply because they're going so fast. Sometimes they show up, sometimes they don't. See how it looks like it's skipping them? It's not actually doing that. I can see the lights going on the box. If I slow this down, then you might see them staying on. you might actually see them go on. 7. Oh, see, we didn't see 8 that time. There's the first one, there's the second one, there's the third one, there's the fourth one, there's the fifth one. Okay, I slowed the speed way down so the screen could keep up. Now notice I used the in process bit. So two very important bits that you see here. Process complete. So if you're sequencing moves, you just use the process complete bit, PC bit, from one motion axis move to start the next one. If you want to do things during the move, you can use the in process bit. You can also use that bit along with other conditions like position. During that position or that move right there, you could actually look at the position at it, and at certain points during that position do certain functions. So once you learn how to use the PC and the IP bit, you're pretty much on your way with motion, and of course the reset, you know, the fault reset stuff. So I'm going to stop this because I'm tired of it, and I'm holding down the button, and of course we slowed it way down, so I'm going to speed it up. It finished. Now we really are going to get our geek on, and we're going to add some bling bling. We're going to add in some flashing. Pause, make the changes, and come. We've made our changes. Now let's run this. Unfortunately, again, it's going so fast we can't follow it, so I'll slow it down. It's still going so fast you can't see it blinking on and off. Now the lights, you can see them blinking on and off very plainly on the hardware trainer, but on the screen here you're not going to see it. And what I added was what I call a multi-vibrator or an oscillator, whatever you want to call it. I have two timers, one with a preset of 300 thousandths, which is 3/10 of a second and 1/10 of a second. You want the light to flicker. If you make these presets too long, they may not go on and off more than once during a move. So you want to make them as fast as possible, yet still be able to see the light blinking on and off. If the off timer is not done, then start the on timer. When the on timer is done, start the off timer. When the off timer is done, this goes false, resets both timers, and starts over. This goes for 3/10 of a second, that goes for 1/10. So we use the on timer timing bit in each of these rungs while we're in process. For each of these moves, this goes on and off every 4/10 of a second, so to speak, and our lights flash. Now, we only had 5 lights, but we got 6 steps. So let's add one more little piece of code to give us something to indicate rotary index 06. And that's really very simple. I'm going to pause, make the changes, and then come back. I believe that wraps up the lab for motion from the lab manual. You've come this far, you might as well play for a while. Use your imagination. You should be in the mood, and I would stay within these labs and repeat them. Try different things until you know at least the basic instructions and the use of the in-process bit and the process complete bit inside and out. Well, that's all, folks, and I will speak to you in the next lab project. This is our hardware demo. I'm going to push the run index button, and you see the lights flashing for the first index. I'm going to speed up so it goes a little faster. You can see it stepping through. Now all 5 lights are lit as it comes back to the beginning. That's going through again, sequencing one at a time. You probably recognize this trainer from the advanced trainer. I need to rebuild this. I would not use these analog meters again. I bought a whole bunch of little digital meters, and I would like LEDs that aren't quite so bright. It's amazing how much light these LEDs produce. And there's index 6 again, coming back to the beginning position. That concludes part 3, the final section of the lab on motion with the Logix engine. Thank you for watching.